of each of them added. We'll look at a couple of easy ones. Definitely. Can anyone remember the up this room on the other side. Just walk in and walk back out again. You don't want to get involved with this class, does he? Obviously. E to the power of infinity. You're guessing. What I'd say, use your calculators, try it. E to the power of infinity. Can't do it, can you? You don't know what it is. How does that function work? E to the power of. Y equals e to the power of any number. How does that work? What does it look like? Looks like that. So what's e to the power of infinity? This is gradually approaching 0. So as gradually approaching 0, e to the power of infinity must be 0. That's something you kind of got to remember, really. So that's minus 1 over s times 0 minus 1. Now if we multiply out those brackets, what are we left with? Minus 1 times minus 1 over s is minus 1 in there times minus 1 over s over s. So the plus transform of the number 1 is 1 over s. Yeah. Having looked at the number 1, what about if we want to represent a DC voltage or current? How would we represent that? We could represent that as a constant. So 10 volts, 8 volts, 3 volts. So we're looking at finding the Laplace transform of a constant K. So we're saying that the Laplace transform of K is integral between 0 and infinity e to the minus st times K dt. What we can do here is apply a constant multiplier. So we end up with Fs is equal to K times the integral between 0 and infinity of e to the minus st dt. Okay, and we've just now found out that bit is, that bit equals 1 over s. Yeah? So no need to do that again. That's what it equals. Therefore, for any constant, the Laplace transform of that constant is the constant divided by s. Other competent mathematicians have done that for a whole host of functions, and these are the ones that we're interested in. So I'm not proposing to do any more finding the Laplace transform of a particular basic function, because what we're really interested in is using this table to solve circuit problems. So if you look at that, we've already got these two are the ones that this is the one that we've just done. The Laplace function of a constant a is a over s. A ramp function is a times t. A ramp is if we were putting in a voltage that is increasing over time, like so, we'd use a over s squared for that. We've got exponential decay, the Laplace transform function, sine wave, cosine, damped sine wave. Not sure we'll use that one, but that's there for completeness anyway, the damped cosine wave. Okay? So, but we'll certainly be doing ones that involve the damped sine wave. Alright? So they look quite complex at the moment, but as we go through the next 3 or 4 weeks, they won't be as complex. They're not too bad. Right? So once we get some notes to you, you'll have that table, and that'll be your reference for the next few weeks, and that table will be in the exam paper. All right? Down the bottom, you've got the Laplace transforms for the 3 circuit components we're going to consider. So a resistor, when you transfer a resistor, it stays with its same value, but you'll notice the units disappear. Units are not involved once you switch to the S domain. Okay? An inductor is the inductance in henries multiplied by S. The capacitor is 1 over CS, where we're talking about the capacitance in farads. The tricky thing about that is most real circuits, farads is in a right small number, microfarad size units, which makes that a little bit more tricky. But we'll start off using some unrealistic but single digit capacitors just to make the maths a little bit easier to start. Alright? Again, notice that once we transferred the component values, the units disappear, we don't use them, but once we transfer back, you need units again. So, let's have a look at our first circuit. We're going to look at the first part of the first step this week, and that is the circuit without a source and getting the impedance of that circuit into the S domain. Okay? So we need to get what the impedance in the S domain is. So R in series with L. What would be in the time domain? How do we express the impedance of that? What's the impedance of 10 ohm resistor? How would we express that in in letters. Forget about these two numbers at the moment. How do we express the impedance of a resistor? Just R plus XL. And what's another way to express XL? Yeah, or omega L, with the omega being the 2 pi f bit. Yeah? Okay? Because XL is equal to omega times L, isn't it? From the table of transforms, the resistor in S space is equal to R, and the C in the S space is equal to 1 over, oh hang on, we've not got C, have we? We've got L. Jumping ahead of myself. And L is equal to L times S. So therefore we can say Z, the total impedance in the S domain, is equal to R plus LS. In the case of this circuit, it's 10 ohms plus 2S. So for a series circuit, the component values in S space are added together like they would be in the time domain. Yep. Two impedances in series. And for that simple circuit, there's no need to do anything else with that impedance regarding simplification or rearranging of. Right, everyone got that one down? Yeah. So, for a simple RC circuit, in time domain, how would that be ZT? R plus 1 over omega C. We have kind of let one thing slip here. Technically there should be a J in there, and that one should be a minus 1 times, which would make that a minus. And in the one up above, technically that should have a J on the end there. Yeah. From table, yep. Therefore, Z in the S domain is equal to R plus 1 over CS, and in this case that is 10 plus 1 over 2 S. Okay, so two relatively easy circuits to deal with. There's an R and an L in series, and an R and C in series. Okay, so far? Yeah. Okay. What about a resistor and an inductor in parallel? Rs is equal to 5. Ls is equal to 0.2 S. But how would we express the total impedance for that circuit? Just with the letters for the minute. In S space. Connected in parallel, remember? Well, yeah, you're working out impedance. So what's the formula we use for two impedances in parallel? Product over sum. So we're looking at R times Ls over R plus Ls. So that's anything we can do with that? Yeah, S on the top, 1S, what is 1? Remember that's 5 times 0.2 times S. That's 1S, isn't it? Yeah. Over 5 plus 0.2S. Okay. There's one further thing that most often is worth doing with this circuit, and that is in the denominator and no coefficient. What we're saying here is how can we make that just S? Divide the top by 0.2, or we'll turn 0.2 into 1. Multiply by 5. So if we're going to multiply that by 5, we have to multiply everything by 5. So that becomes 5S on the top, 25 there, and S there. I did warn you about 5s and S's. try to think of as another better letter of the alphabet that you could use that wouldn't get confused with any numbers, but S is the one they've decided is the one to use. So that's R and L in parallel circuit and manipulation. Have a go at writing the initial expression without any simplification for R and C in parallel. Right, first of all, what's the expression, letters only, for the total impedance in that S domain? R times 1 over CS and so therefore when we put the numbers in we get 10 times 1 over CS divided by 10 plus 1 over CS. Oh, hang on. Should have been putting numbers in here, shouldn't I? 4S and 4S. Right, Jack. Is that what you meant? Yeah, I can see how that's confusing. Sorry. Yeah, I think I better stop writing that like that, because what we're saying is the capacitor in S space is equal to 1 over what the capacitance value is in farads times S. So I've done it right, but I can see where you're getting confused. Because you yeah, perhaps I should put here, would it help if I said that was ZC, the impedance of the capacitor in S space, because that's what it is. Do you see how I keep adding letters and that get even more confusion? But that, what I've done there, I can assure you is correct. Okay, and I'm only putting this bit in at the moment just to reinforce we get the values from the table. Once you've got used to it, I shan't write that anymore anyway. Okay, I won't do it anymore. But I can see what you're saying. My fault. Think of a new way of writing it. Okay, so that's correct. So the impedance of the capacitor, impedance of the resistor, multiplied together over the resistor, capacitor, add it. So, what can we do to simplify that? What can we do with the top line? 10 times 1 over 4 S is... Sorry? I wouldn't do that yet. And write it like that, yeah? You'll see why in a minute, Ed. Alright, 10 plus 1 over 4 S. We need to get rid of the fraction on the top. If I was to write the denominator as a fraction, what would I put underneath it? All that is the denominator. If I was to write that as a fraction, what would I put underneath that red line? And that will still equal 10 plus 1 over 4s. Forget that top line for a minute. What do I put under there? I put 1 under it, won't I? Yeah? Alright, you lot like laughing at me, don't you? Do you agree with that? Yeah? So how do we divide fractions? Going back all them years ago when you were done adding, multiplying, dividing fractions. We got a fraction on top divided by another fraction underneath. What do we do to multiply, to divide two fractions? Be a bit more careful about what you said there, Robbie. Flip the denominator and multiply. So what we do is we say is equal to 10 over 4s times 1 over 10 plus 1 over 4s. Multiplying those two together gives us, top line, 10, bottom line, 4s, outside some brackets, 10 plus 1 over 4s. You're going to see in a minute, Ed, why you don't get rid of that 4 up the top there. Can you see it now? What happens when we multiply out the brackets? 4s times 10, 40s, plus 4s divided by 4s, which equals 10 plus. Follow that, everyone? So we put a little note in what we've done at each stage there. Flip denominator and multiply to that. Multiply out the brackets and simplify. We've gone from that up the top there, our initial effort, this one, to that down the bottom there. And if you just quickly look back at the table and see why you might want to do all of that, is if you look at all these transforms here, there's only one that's got an S on the top. And that's the damped cosine wave that I said we probably won't use anyway. Okay, so you're often looking to get any kind of S away from the numerator. It certainly will be when you're added in and written a function for the current, which is what we're generally going to be finding is a function for the current that we can transfer back. You're going to be looking to try and make that function on the right hand side look like one of these, so you can transfer it back to the time domain. Yep. So at the moment we got something that looks like that at the moment, but we haven't added a voltage. That comes next week, I'm pleased to know. Alright? All okay with that? So, expression for, write yourselves an expression for the total impedance of that RLC circuit in the S domain. No simplification at this stage. ZS is equal to, just the letters for now, R plus LS plus 1 over CS. So put the numbers in. It's 3 plus 1.2 S plus 1 over 0.5 S. Can you see any immediate simplification that you could do? Quite a lively class this afternoon. What could we do to that fraction on the far end? No, you can't add that and that together, but you can do this. 3 plus 1.2s plus 2 over s. You can divide the 1 by 0.5. Right, however, we need to have fraction form with a common So we want to be able to do that and have a common denominator underneath S. So the last bit is easy. How do we make that 2 over S? We just put 2 in there. What do we have to do to this bit to make it right? Square it, yeah. 1.2 S squared. Yeah. These work. But it's got to be a perfect square in the end. Not next week, the week after maybe. Right? Yeah? That comes, the common denominator being S comes from the fact that these are over 1, and you get a common denominator by multiplying all the denominators together, you should remember. So 1 times 1 times S gives us a common denominator, S there. Yeah, everyone happy with that? Yeah. And then what we've done at the bottom, we have to do at the top. So. Okay? Right. Now, up until now, we've had capacitor values that are largely unrealistic. Even half a farad is a massive, great capacitor. Certainly 2 or 3 farads you're not going to come across. So it can get a little bit more tricky. Have a go yourselves at that one, where we've got a 2000 microfarad capacitor, and even that's a biggie. Okay, but have a go at that one on your own. Process through that you've just done. So we got an answer for the total impedance in S space for an RLC circuit in terms of the resistor value, the inductor value, and the capacitor value. How do we go about for RLC then? Yeah, I know, maybe you just give me the answer, but what's the process? No, there's no numbers. General solution. So what did we do? When this was a number, what did we do? Yes, so we multiplied, we divided 1 by the number that was C, didn't we? So we need to write that as R plus LS plus 1 over C over S. Yep. And then we simply want a common denominator of S. So this becomes R times S. This becomes L times S squared. And this becomes 1 over C. General solution, what it's saying is the impedance in S space is reliant on the resistance value, is dependent on the resistance value, it's dependent on the square of the inductor value, and it's dependent on 1 over the capacitance value. What general solutions can help you to do? If you've done the whole transform thing and you've got an expression for the current, if you get a general solution for the current, you can then use graphing software to look at changing the constant values RL and C and see what difference different values make to the response. So by having a general solution, that gives you some flexibility there to see what happens when you change those values RL and C in the circuit. Okay, so have a go and see if you can write a general solution for the RL and the RC circuits that we did earlier. And that's easier than that one. Okay, that one's dead easy. They probably both are actually. And the RL in parallel. So we can write general solutions for all of them. You realise how simple these two were. before I put them up there, but Z S is simply, in general terms, R plus LS. Can't simplify that any more than that, and this one is ZS is equal to R plus 1 over CS. They are general solutions in their own right, made simple by the fact there's a series circuit. They're just added together. What about this one? How do we express that? And then what operations did we do after that on that circuit? Yep. So we divided through by, to do that, how do we get S on its own? Divide through by L. We have to do exactly what we did when we had the numbers in there. We divided through by 0.2, didn't we? Yep, because that was 0.2 S there. We wanted that just S on its own. We divide that through by 0.2, we end up with just S, don't we? So we have R over L plus S. What about the top line? It ended up just as R times S, didn't it? 5. Yeah. Okay. You do the same processes as you did when you had the numbers there to get the general solution. What about RC? ZS is equal to R times 1 over CS over R plus 1 over CS. Then what did I do? Simplified the numerator. That number R was 10, so I wrote it as 10 over CS all over that bit. Sorry? Yeah. And then we multiplied out, didn't we? ZS is R over CS times 1 over R plus 1 over CS. turned that bottom fraction upside down and multiplied to do the division. That becomes R on top, CS times R plus 1 over CS in brackets. And then multiply the brackets. R on top, CS times R plus 1. It's just about following the same algebraic manipulation as you did when you had the numbers there, but you haven't got no numbers, so you just got to do the letters, but do exactly the same process. Alright?